you have to decide, best as you can judge, what the elevation angle is that you're interested in. On 160 meters, it's probably up around 20 degrees. On 8 without RDF actually is. And here's some ranking of some of the antennas we'll talk about. We'll talk about all of these antennas briefly and give you some clues as to how to learn more. The smallest, very useful antenna for receiving, small diameter loop, can be as small as 3 feet in diameter. The size of the loop mainly determines how lossy it is. The smaller the small loop is, the less signal gain there is. You can make that up with a high gain preamp. It can be as small as about 3 feet in diameter, about as big as 12 feet in diameter, and then its performance starts to fall off. And then from there, believe it or not, notice this, it's not a typo. Small diameter loop, some people call it a magnetic loop, has an RDF computed this way of about 4 dB. A little bit better, believe it or not, is a single vertical. Well, how can that be? Well, look at the definition. It's the gain at the desired azimuth and elevation angle compared to the entire hemisphere. And a vertical has very, very poor response at very high angles. So it actually has directivity. It's omnidirectional at relatively low angles, but at high angles it has a deep null. So it's RDF. It's actually, for a very simple antenna, its RDF isn't bad. And then we go to short beverages and beverages on the ground that tend to be in this range, a little bit better. And then arrays of small loops, flags, pennants, U's, the K9A loop, AY loop, the shared apex loop array. These are quite small antennas. And the performance is useful for a small antenna. They have a well-formed main lobe. They have reasonably low side lobes and in a very tiny space. Not as tiny as 3 feet, but much smaller than a beverage. And then the next level of performance there is just 2 short verticals, and I'll show you how to build those. Either simply 2 or 2 of those in a triangle with only 65-foot spacing on 160 meters. And now you're getting up in the range of a beverage antenna with just 2 short verticals. And then probably the most popular receiving antenna, it's been around for nearly 100 years. I'll show you the patent. 500 to 600 foot beverage, nothing critical about the length. And now we're up around 10 dB RDF. The next one, a lot of people think it was invented about 15 years ago when it was presented at Dayton. Well, that's not true. It was also invented about 90 years ago. 2 beverages, close spaced, and staggered by a quarter wavelength. You pick up another dB or so with that. A very worthwhile dB. It's a deep null steerable off the back. And then quite a long beverage. Now we're getting into real performance. But look at this one. A 4-square array of 4 verticals, only 65 feet on the side. That takes 1/10 of an acre. And look where it ranks relative to the other antennas. Only a few dB down from an antenna that takes 20 acres. And better performance than a 500 to 600 foot beverage. So this is a real sweet spot. Most people can install something like this, and you can even buy it commercially. You can buy all the parts. If you're not into building antennas, you can buy this thing. And then you can, the next step in performance above this quite compact array takes some acreage. Not surprisingly, it's 4 verticals, bigger space, and all the way up to something was also invented 90 years ago, broadside phased beverages, taking a lot of space. Size matters, but you could do amazing things in a small space. All of these antennas fall into about 3 categories. And in fact, if you look at the theory of them in detail, they're all kind of the same. They're all verticals. Believe it or not, these are all verticals. A loop antenna basically is they operate as vertical polarization, and the very small loops, the magnetic loop, its benefit in our world is a very, very deep null off the ends. And the way that works is the two sides of the loop are 180 degrees out of phase, and that creates an extremely deep null off the ends. So even though it's a loop, its performance is really best analyzed as 2 very, very tiny verticals close together. And similarly with the larger loops, they could be modeled as very short verticals using the horizontal part of the loop to interconnect the verticals. So these are all vertically polarized antennas. These are all quite small. Beverage antennas are also vertically polarized. There's a whole range of them. We'll talk about every one of these. And then my favorite antennas, arrays of short verticals, and these have become very popular with the advent of the high Z arrays, where you can go out to DX Engineering, give them your credit card number, and you'll have the antenna on your doorstep when you get back home from Dayton. Okay, so let's start with the smallest one. No matter how small your available space is, you have room for one of these. This is a very specialized antenna. There's only one thing that it does well. Only one thing. And that is nulling single RFI source. This antenna, properly built, has an extremely deep null off the ends of the loop. Extremely deep. And it's not difficult to build this antenna. So if your challenge on 160 meters is one RFI source, or let's say you've got multiple RFI sources, but one of them is more problematic than another. It's the strongest one. You really want to get rid of that one. You build a small diameter loop. It probably won't take you more than 2 hours to build your own, and orient it such that the end of the loop is pointed towards this ground wave RFI source, and this antenna will null it right out. It will be gone. This antenna is omnidirectional for horizontal polarization, and it's essentially omnidirectional other than these 2 very deep nulls off the side. The width of the null, in terms of its depth, is only a few degrees at its deepest point, and at minus 3 dB down, that null is only about 20 degrees wide. So it's essentially omnidirectional except towards the RFI source. This antenna also requires a preamp. It doesn't need to be exceptionally high dynamic range because the sensitivity of the antenna is very, very low, but it definitely needs a preamp. And in order to get the best possible performance on this, you really have to worry about isolating the antenna from everything that connects to it. So if it has a DC source going to a preamp at the feed point, for example, you really need to isolate that very well. The feed line has to be isolated very well. If it's a permanent installation, it's a good idea to bury those cables, just to be sure that the signals you're receiving are coming in from the loop and not from the feed line, not from control lines, not from DC power cables. And this, by the way, is true of all of the low sensitivity antennas. Isolation is really important. And here's how simple it is to build this thing. Here's a website showing this loop and how to build it. And you can find other sources on the web of all kinds of designs of loop antennas. But it doesn't need to be any more complicated than going to the hardware store, buying some copper tubing. This silly little thing is sometimes called a coupling loop. Well, it's not really. I think people that build antennas might, this can be in any shape at all. They might call it a hairpin if we happen to be building a Yagi. All that does is, this loop is continuously conductive. So if you start here, it goes all the way around the loop and then through the little hairpin, I prefer to call it, because that's really its function. So it's a continuously conductive loop, and the receiving voltage is picked off of a somewhat higher impedance because of the placement of this hairpin. So instead of having a tiny, tiny fraction of an ohm here, by placing this hairpin there, you raise the impedance a little bit. See, the signal levels are a little bit higher. That's all this is. And a little variable capacitor to resonate this whole thing. That's all there is to it. The details are here.
What's the size of the pipe?
It doesn't matter.
It doesn't matter, okay.
It doesn't matter. As long as it's mechanically strong enough to withstand your use. This is a very nice antenna, by the way, for finding noise sources. This is a really, really good antenna if you want to find RFI that's bothering you on 160 meters or 80 meters. An antenna like this has usable sensitivity for direction finding RFI all the way up into the 20-meter range. And then above that, its sensitivity gets to be really poor. I think for almost any serious 160 operator, we occasionally run into problems with RFI, and we say, gee, how am I going to DF this thing? Well, this is a good way to find it, is with a receiving loop. If you don't have one, spend 2 hours in your shop and you'll have one. Okay, small loops. These are the smallest antennas that provide useful directivity for skywave signals, for signals other than locally generated, other than eliminating locally generated RFI. And these are the smallest ones, the K9AY loops. We'll look at those in a little more detail. This is a relatively new array. It's been around for a couple of years. There's going to be a presentation on the shared apex loop array at the Antenna Forum on Friday. So if you're interested in this one, go to the Antenna Forum. I won't spend a lot of time on it because you'll learn a lot more at the Antenna Forum than you could ever learn from me in a couple of minutes. All of these have the same problem. They all produce low signal levels and need a good preamp and careful attention to stray signals that could get into the antenna from any cables that are connected to it. And if you need to know how to do isolation, you can learn lots about that by going on Google and reading about it. So the K9A loops you can buy from Array Solutions. There's the website. It's tiny, 25-foot by 25-foot square footprint. It has useful directivity for skywave signals. So you can select the European direction for this, and it provides useful reduction in noise levels coming from other directions. Not only locally generated RFI, but also skywave propagated signals from thunderstorms. If you're trying to work FT5ZM and there's a guy in Texas that's bothering you, it'll knock his signal down. So this is a very tiny antenna. Most people can fit this in their available property. A little bit bigger is the shared apex loop array. Let me contrast two things. The beam width of the K9AY loop is about 120 degrees. It's useful beam width. It's a little bit bigger than a full-size 4-square array. And the K9 and the shared apex loop array is more like 75 degrees, so its beam width is usefully narrower. RDF is slightly better. And these arrays are also have been taken on the expedition, so you can carry these things in a reasonably small space. So Antenna Forum tomorrow, if you want to learn more about it, you can buy it from Array Solutions. There's the part number. Okay, so let's go to a not-so-new antenna, the Beverage. This is the patent. So the patent was filed almost exactly 100 years ago. 94 years ago, the patent was filed. Beverage developed this antenna during World War I. The Germans cut all of the transatlantic telegraph cables, so the only way for U.S. forces to communicate with forces in Europe was by radio, and the only transatlantic means of communicating by radio at that time was long wave, down around 50 kilohertz or so. That was it. several 100-kilowatt transmitters, and nobody had any serious capability to provide directive receiving antennas. And Beverage invented this thing. It was kind of by accident. He strung a wire out on the ground. So his original version was a Beverage on the ground. So bog is something Beverage would appreciate, because that was his first Beverage. He was a very, very capable and experienced electrical engineer at the time. So he knew that if he was going to lay a wire on the ground, he better find a place where there's a lot of sand. So he laid it on sand. And he did a lot of measurements of the performance of this thing, finally wound up optimizing it by, on those frequencies, putting it up on telephone poles that looked like a telegraph line. And ultimately, several years later, filed a patent in 1920. So this is the Beverage we recognize. It's on 160 meters, probably the most common ones are 500 to 700 feet long. Get good RDF. It's useful to go longer if you have the space. It's important to know that if you go beyond about 900 feet with a Beverage, very frequently its performance is degraded. And the reason for that is that the velocity factor of the Beverage is kind of like the velocity factor of like a transmission line. So it's a relatively slow wave antenna. So when the antenna gets to be too long, signals received at one end of the antenna are actually in the wrong phase relationship with signals received at the opposite end of the antenna. So its performance degrades. So I'm not suggesting that if you've got room for really long Beverages, you shouldn't put them up, but you need to follow one of W3LPL's rules, and that is you can never have too many antennas. And in this case, if you have a really long Beverage, you better have a way to get to a shorter Beverage too. Well, there's a corollary to the you can never have too many antenna rule, and that is unless they're too close together and they interfere with each other. Then you can have too many. So the single wire Beverage is a fabulous receiving antenna. It's the simplest of all of these. And it's not very hard to take 500 feet of wire, find a way to suspend it in the air, point it in the right direction. You've got a fabulous receiving antenna, and there's almost nothing you can do to make it not work. So it takes space, but it is dead simple. You can teach a 10-year-old kid how to build this thing and be successful. Beverage on the ground, its performance, of course, is not as good as a Beverage that's 6 or 7 feet high. You start to run into velocity factor problems beyond about 220 feet on 160, where signals received at one end of the Beverage are in the wrong phase relationship with signals received at the other end. The velocity factor of this antenna is very low. But it is a simple antenna, takes a small space, has useful directivity, and there's a website that tells you all the details about how to build one and use one. People have used them with good success. Yes, and please identify your name and call sign.
Thanks, Frank. Pete, KUTC. Frank, this raises my question of the impact on ground conductivity on Beverage antennas. Take a salt marsh versus high desert.
Right. A Beverage antenna, let's go back to this 90-year-old drawing. This antenna was originally intended for very low frequencies, around 50 kilohertz. It was miles long, and it relied upon the lossy ground under the antenna to develop something called wave tilt that actually causes the incoming signal to be tilted. Well, we're not interested in building Beverages that are 10 miles long. We're interested in maybe building one that's 500 feet long, and we're also operating in the medium frequency and high frequency range. Well, where do we get wave tilt from at that frequency range? We get wave tilt because the DX signals we're interested in don't arrive right on the horizon, they arrive above the horizon. So for the most part, Beverage antennas for HF are relatively insensitive to the ground conditions because the signals always arrive above the horizon. Now, Having said that, I have heard anecdotes from people that have gone on de-expeditions and attempted to install beverages on highly conductive areas, over salt marshes, over a beach next to the water, and they have reported that the beverage antenna performance was very poor. So all I can say is, if you live on a salt marsh, don't put the beverage over the salt marsh. But apart from that, don't worry about it, because the signals at HF always arrive above the horizon. And they will induce a signal in this wire because they're arriving above the horizon, and they will build a voltage gradient along this antenna. So don't worry about it unless you're W1KM and you have a salt marsh for your property. Okay, so Beverage Underground, you can learn everything you need to know about it here. It's a really good website. Two-directional switchable beverage. Patented in 1921. It's been around for a while. The design's about the same, you can buy these from DX Engineering and other sources. A transformer at each end. What this antenna does is it uses the two wires for receiving as well as a transmission line to send signals back from the far end. And with a bidirectional beverage, you can either switch it so you can listen to one direction or the other, or the very best way to do it is to bring both signals back to the shack. Bring two cables back, and then use a variable phase controller, and you can steer the null off the back. And I'll show you the device that does that. So if you're going to go to the trouble of putting up a two-wire beverage or a bidirectional beverage, my recommendation is, instead of switching, let's say, northeast or southwest, bring both signals back and use both of those in a variable phase controller. This was presented at Dayton about 15 years ago, and everybody said, wow, this is a breakthrough. We've never learned how to do this before. We take two beverages, stagger them 90 degrees apart, phase them in the right way, and then we have a steerable null off the back. Sorry, it was patented in 1927. This was developed for the first transatlantic radio telephone circuit from New York to London. The receiving end of that circuit was in Maine. And this antenna was developed by RCA and GE for that transatlantic single sideband radio telephone circuit. But you know, they have lots of room in Maine. I don't think they have developed this idea of RDF yet, but they did know a lot about antennas, particularly Harold Beverage. So with this antenna, of course, they also discovered that they could steer the null. They brought both signals back, actually, to their receiving hut. And that receiving hut is still there. It's on the Canadian border, about 2 miles. It's on Interstate 95, about 2 miles west of the Canadian border. The building's still there. The basement is all lined with copper, where their equipment was. So they said, well, we've got lots of room. We can probably do better than two beverages. So they invented in 1927 something that Hams thought they had done recently. They took 4 beverages, staggered 90 degrees, and then spaced 5/8 of a wavelength apart, and brought all those receivers back to this building on Interstate 95 on the Canadian border, and that was the receiving antenna for the transatlantic radio telephone circuit in 1927. 14 dB RDF. Sure, if we could tell Beverage about that, he'd be interested in how that was computed. But this is really a fabulous antenna. You could build your own for 160 meters. It takes 20 acres. And it only covers one direction. It's a great antenna.